Hello and welcome back to the lab. Today on the bench we have my Agilent 53131A. This is the older frequency counter we have in the lab. If you roll back into the historical record of the channel for 2,000 subscribers, I think it was the 2,000 subscriber video, we picked up a 53230A frequency counter that we're going to do some 10 megahertz references on and a couple of other things. So we got some cool stuff coming to the channel. There's been a few videos on this unit. One was we added the third channel. I didn't have one of those when it shipped in. But one of the nice things about this particular frequency counter is it has the high stability time base in it. So even though this isn't the 3.2, which is a more accurate frequency counter, it does have the high stability oven. At the time I picked this frequency counter up, I was completely unable to calibrate it. I had to trust it as is, and that very quickly led me down the path of 10 megahertz lab references, things like that, because picking this up from the secondary market, I had concerns about the accuracy of the crystal. Had anybody been in it? Had it drifted? Things like that. So I needed a more stable, a more trustworthy time base than the internal crystal on this one to get started, especially because one of the functions was calibrating a 184, a couple of other things that were going to spread timing information to other units. I had to make sure that was right. So what we ended up doing is I ended up getting a GPS-DO and hooking it up to the back side of this and using that output as an external reference. That tightened up the timing a little bit more, but the GPS-DO was a little drifty back and forth as it was servoing to stay in sync with the GPS satellites. So the GPS-DO gave me long-term stability. However, I needed something for short-term stability. What we ended up doing there, we picked up this guy, a Stanford Research Systems rubidium unit. That gave me the short-term stability. Now, the way I'm running the lab, because the rubidium will drift over time, you do need to periodically calibrate it as a source, or it has a 1 pulse per second sync to it. So I'm taking the 1 PPS out of the GPS-DO, feeding that into the rubidium source. That's stabilizing the rubidium source. The rubidium source is stabilizing the GPS source. So now I have a very stable, self-updating external clock that a lot of my RF gear can talk to. That's actually an option 3 unit. So it has all the amplifiers on the back, so I have plenty of 10 megahertz ports. Now, that's the long way of saying I can now align the high stability oven in this unit. I have a stable enough clock in the lab where we can do that internally, and everything can be good to go. So what we're going to do today is we're going to tear into this. The cal seals are already busted because I've been in here because we installed the third channel. But what we're going to do is we are going to actually do a capacitor refresh on this unit. These particular units came from a time where capacitors were horrific in terms of their reliability, especially in the time frame that I suspect this unit was made. I lost count of how many computer motherboards and consumer electronics I had to recap. It was an everyday thing. Soldering iron was in my hand hours and hours and hours a day, and it was just what we were doing because they were just failing left and right. I mean, this was all consumer electronics, computers, TVs, motherboards, didn't matter. Caps were just a problem. And that was in the late 90s to late aughts range where it was awful. We're going to do a cap refresh on this. Hopefully these haven't leaked. I was talking with another fellow YouTuber through some of the news group, email groups, and I found out his was leaking, so I'm hoping I don't open mine and find the same problem, in which case we're going to have to clean up the board and make sure, because the electrolyte that's in those caps can do horrific damage to the boards, even to the point of making them unsalvageable. So let's get in it, hope for the best, and we'll make this thing stand the test of time. I also want to keep this running for the lab because this is a frequency readout for one of my scopes, as well as my general bumming around frequency counter but I don't want to have to start up the 53230. So, let's get into it. Good old HP gear is rather easy to get into, so on this one we just have to pull off this. Oh, that sounded horrible, but it's fine. The bumpers. And then it's going to be 3 screws, these 2 in the back, 1 on the bottom, and the unit will punch out the front. The front bumper does not have to come off because it will come out with the unit. Alright, we'll do this here in real time. The one goofy part is they do use 2 different size Torx bits. The small screws are T15. The larger screws are the larger screw, I should say, is a T20. This will pop off. This should come out. There we go. And now, I already see the clock. And there's some early aughts or mid-aughts construction. Here's going to be the crystal oven. We have a 6160, which I believe is the better time base. The card that was added was this card in the previous video, so that added my 3 gigahertz channel. This is one of the caps that I'm worried about. These are the rest of them. So we have a switch mode power supply. This will be switching transformer, output regulators, rectifier. This is probably going to be the switching transistor, control and regulation circuits. So we are going to need to get this board out. I'm also probably going to change this capacitor too. This looks like it might be, this might be a REFA cap. I'm not 100% sure about that yet. But I have some XY capacitors to put there if we need to. And it does look like this module can actually come completely out, so we can, there's a power connector under there. This screw, that screw, probably some on the back panel. And then this whole module should lift out for servicing, which would be very nice. Not a bad design. So, let me get this power module out, and then we'll take a look at it. Okay, with the power supply out, it exposes the board. Here's the main power connector to the logic board. We do have this cap, which is going to be in question. Here's our crystal, ovenized crystal oscillator, the high stability, which is option 010. So it's the middle oven. It's not the ultra stability oven, but it is the high stability oven. Now, if you did not have any of the upgraded time base options, this is your time base right here. So this would be Y2. This is a 10 megahertz crystal, so that's what's actually going to be driving the main clock of the frequency counter. The core of any frequency counter is the time base. It can only be as stable as the time base goes. The front end circuitry can compensate for or improving the front end circuitry can improve the readings if the stability of the time base is good. You can have the best front end of the world and a wobbly time base, and it's not going to give good results. So if you did have none of the time base options, a external reference can really tighten up the readings of the unit, which is actually what we did with the 53230A. Because I have a rubidium source, we're using that as the external unit. I did not order the 53200 with a time base option because I don't plan on using that away from the lab. I do want to adjust this time base because if I do have to take a frequency counter anywhere on site, maybe do some radio servicing or anything like that, I'll probably take this one with me because it actually has a better time base. So even though I have a much better frequency counter, the way this is optioned up, this would actually be more stable if I was away from the lab. If I'm in the lab, the 230A is going to be the most accurate I can be. Okay, the good news and the bad news. The first capacitor we're going to tackle is going to be the one that's on the main logic board, which on the back side would be right here. Front side is going to be right there. Is that a boost or a buck converter up here? That's kind of what it looks like. So this might be the bulk cap for that. We'll have to see what that is. That might be another capacitor. I'm not 100%. No, that's a choke. Okay, we don't need to worry about that. Just this one. Everything else is tantalum and ceramic, so it's not going to be a problem. But good news is we can get to it without taking the board out of the frame. Bad news is some of these pins are a little crusty, so I'm not... no, it's not going to really pick up the crust that I'm seeing that well, so really hope we don't have any damage. Okay, this dates from an era with the start of ROHS. For those unfamiliar with the industrial terminology, that was the reduction in hazardous materials, which ultimately was lead and mercury and IT stuff. So what we're going to do is, because this probably has the early stages of lead-free solder, going to add a bit of leaded solder to make this behave better when we hit it with a desoldering tool. And just because we can, we are working under nitrogen. Most definitely not something necessary, but we've got it, so why not use it? Okay, so our negative side is to this side of the board. All right, no crust. Looks like we're catching it just in time. I see a little bit, tiny bit of electrolyte starting to leak out on the bottom of the cap. So it looks like we're catching it just in time. So now I got to clean that very well. We have a trace that runs underneath the cap. Actually, we have two traces that run underneath the cap on this side of the board. We have another trace that runs underneath the cap near the negative lead on this side of the board. We have another trace that goes to this resistor from the capacitor from that side of the board. So there's a lot of damage. The electrolyte will just sink through the through holes. It'll eat through the board. It is really awful, the kind of damage it can do. Starting in on the switch mode power supply, I am running into some physical limitations. I'm not having exactly the right value and exactly the right caps in stock, so I am going to have to put in an order for some stuff. So hopefully we can get through the power supply without too much trouble. Some of these joints are quite tight. Since I've finished up the small stuff that was over here. We had this cap that needed to be replaced, this one here. I can identify them because I haven't cleaned the flux off yet. But since I've started working in this area where this is the high current, low voltage side, so the traces get really fat because of the current carrying capabilities of it. Also, the capacitors go from 50 volt caps to 16 volt caps. I've switched out the tip on the soldering iron. So traditionally, I use a fine point iron tip. It is not conical. It is a chisel tip, but it is a very fine chisel tip. I find that to be good for most general purpose soldering. However, with the wrong iron. Now I need to not burn myself because this one's actually on. I've gone to a fatter chisel tip. Reason being the traces are going to soak a lot more heat out of the iron, so I wanted more thermal mass in the iron so I could get better solder joints and not have to worry about cold joints. Okay, I've got the power supply reinstalled. I am going to have to order some capacitors. I need a replacement for this guy, which I do not have, and a couple more on the board. On the power supply board need to be replaced still as well. But since we're here, I figured, and I have to wait, I figured it would be a good idea to do a test power up of the board just to check our progress. This was a working unit before we started, so not too concerned about starting it up. Open, so we're going to power this on, and after I plug this in, I'm going to be very careful because I believe, yeah, this does draw some current, standby current, so we're drawing about 19 milliamps, about 600 milliwatts at the moment in standby power, so this is not a completely off unit because it does keep the crystal oven warm and a few other things. So we're going to turn it on. Okay, let's talk about this thing, because I'll be honest, this thing has been kicking my butt for about 3 hours. But I think we finally made some headway. So, in the last clip, you guys saw I powered up the HP unit and nothing happened. So, there's only one thing left to do, which is tear it back down and figure out what I did to break it, because it worked before. So we had a device that was in a known functioning state. I did some work on it. It crapped out. The next logical step is, well, what did I do to screw it up? So I did take a look at just to see if I'd blown up any critical components like the switching transformer or anything like that. What a new power supply would cost. Well, a new power supply cost about $450. And these units still go on eBay for about $1,000. So obviously that was, since we had a fully functioning unit, it was time to give it a go. Hooked up to the main switching transformer, which in this particular unit is over here. You have to be very careful hooking up to that because this is a 300, at least in my area, 160 to 400 volt section, depending on where you are in the world. This cap can see 360 volts if you're in a 230 volt country. For me, it's 165. But I was seeing switching happening, so the power supply was trying to start. It just wasn't. Now the reason the Agilent wasn't trying to start up is this is a soft power button, which means I have to have a standby voltage on here for the counter to start. So, next thing was to come to the pins, measure the voltages. Black is ground. We have 5 volts, 12 volts, negative 12 volts, and then we have a negative 9 volt, which has its own isolated ground over here. And I was getting very little out. I could see it trying to start, but it was very start-stop. Lots of reverse engineering happened. Found out this IC right here is the voltage regulator for the negative 9 volts, even though that's a positive voltage regulator. Don't 100% understand how it's regulating the negative 9, probably just flipping the polarity at the output, which is fine. This cap is destined to be replaced. Had switching going into this circuit, was looking for the 5 volt regulator, because obviously I'm assuming 5 volts is my standby power. It's either going to be 5 or 12. I didn't have either. So I was checking around looking for 5 volts. And I couldn't find a 5 volt regulator. Well, that's because the regulation is actually done in this part and by the opto IC here. So the 5 volt rail is regulated by controlling the switching transistor. So there won't be a 5 volt regulator on these, but if you're missing 5 volts, or if it's not starting at all, this is one of the first ICs to check. Everything's good there. I did check the power supply IC, which is over here. That was getting, can't see it because of the support. This was getting power and ground, and it was actually outputting. That was making it to the switching MOSFET, which was in fact driving the transformer, so I could see switching on the low voltage side of the transformer, so everything in my high voltage switching circuit was at least trying to start, but it really wasn't. Dove into it, was looking around, reverse engineering it, figuring out where things go, what things are what. This is not a regulator IC. This is actually rectifier diodes for the 5-volt rail. This is not the 5-volt regulator. This coming off of here is a thermocouple. I even tested the thermocouple to see if it was tripping it out, thinking it was thermal. Thermocouple functioned fine. I just lifted one of the legs. It's a resistor. It's a temperature specific resistor, so blew some of the hot nitrogen on it and watched it fall in resistance. So that was functioning normally. So everything was looking really good, except the stupid power supply wasn't starting. I even backfed 5 volts into here, see if anything was shorted on the power rails. If you need to troubleshoot one of these power supplies, go through this real quick. A functioning power supply ground and 5 volts. On the 5-volt rail is going to be 25 ohms. 12-volt rail is going to be about 130 ohms. We will reverse the polarity for the negative 12-volt rail, just so we don't damage anything. About 140K or 1.4K ohms once everything stabilizes, and polarity on the negative 9 is about 800 ohms. So you can sanity check a power supply that way just to see if anything on the rails are shorted. Everything was checking out fine. So, but my attention kept getting called to this section here. So I backdated these 2 capacitors because I did replace them with these. And I'm actually we're going to test it and see what happens. I did a test power up and the supply started and worked. I had 5 volts at the connector, which is what I should have. So what we're going to do is we're going to move forward. One of these 2 capacitors, with the new ones that I put in, was preventing the supply from starting. So what we're going to do is, I have a sneaking suspicion it's this one that I think is the 22 microfarad. This might be 2.2 microfarads, and I may have put too big a cap in here. So we're going to swap out the 10 mic, see if it starts. If it starts, we're going to really look at this capacitor, but we're about to go from here. So this is the 10 mic 50. We're going to swap that back out, and then we'll see if we have 5 volts. Okay, we have the 10 mic cap switched back out. We have the 2.2 mic, or what I think is a 22. It might be a 2.2, and that might be part of the problem. Cap that is in place. I'm going to move you up to the meter so you guys see what I see in real time, and then I'm going to plug this in. I have not plugged in the power supply yet, so I do not know which one's going to be which. We're going to find out together. All right, here we go. Plugging in. And we have 5 volts. Okay, so that means the cap that was pissed off was that other capacitor that's down there. So we're going to unplug this, give it a chance to discharge. And I'm going to see if it's not a 2.2, and I just stuck the wrong value in there and spent 3 hours troubleshooting that I didn't have to. Okay, I have our 2.2 microfarad capacitor in there. It is very inconclusive whether this is a 2.2 or a 22. However, it really looks like 2.2. If this is going to focus, it probably won't. So it really looks like 2.2. But we're about to find out. Here we go, plugging in now. 5 volts, okay. So 2.2 it is, not 22. My guess is that's some kind of fault out. If the voltage doesn't rise fast enough, the switcher doesn't come in. So I'm going to put this back in the frame, see if we get a boot up. Okay, 2 things to note. If you have a healthy supply, you should see the fan spinning, which we do. And draws about 21 watts in standby. I'm not 100% sure what that's going to dial down to once it heats up the oven. I'm sure it's going to be a little heavier while it's warming up the oven-controlled oscillator. So well, I'd say that's pretty good. So what we're going to do now is we are going to wait for the additional parts to come in. Everything looks good here, and through the magic of the camera, you guys, it'll be a couple of seconds. For me, it's going to be a couple of days. So when those additional capacitors come in, I'll finish rebuilding this power supply, and then we'll do an alignment on the crystal. Okay, a pile of capacitors gets delivered. So I had to wait far longer than I should have for these. Not 100% sure what happened, but these should have been here days ago. It's a week since the last video. But we have our caps now. So we'll get the board back out and finish up this refresh. Alright, after some quick soldering, out with the old, in with the new. We do have new caps in all positions on this particular power supply. So let's put this guy back in and see how it goes. Hopefully it starts this time. Last time it wasn't so good. I did also replace the one capacitor on the board with a 560. I couldn't get a 470 and 63 volts, so we have a 560 in there, which should be totally fine. All right, let's plug this on and see if it gives us some magic smoke. Well, the fan started, so that's a good sign. We're drawing about 21 watts. Kick it on. Ah, much better than last time. Okay. All right, so we can see how far off it is. I have the rubidium standard plugged into the front end of the unit, and currently it's running about 6 nanoseconds slow. That last valid tag is, so it just servoed back. I was watching it a little bit ago, and it was dead even, so it's still dancing around there a little bit. And I go about plus minus 6 nanoseconds, so that is totally fine. But we are locked to the 1 pulse per second, and everything's good. So, just in the time it took me to talk about the rubidium, we've seen this come down quite a bit. That's the oven warming up in the time base. So this has been off for several weeks, or a week, while I was waiting on parts and things like that. So I need to let this oven warm up before I even do an adjustment. And as you can see, as I'm talking, it's still counting down. So the crystal's heating up, so it's going to kind of coast in. And this should stop right around 10 megahertz. Well, it should stop at exactly 10 megahertz in theory. So we'll figure out how far it is off. But slow the gate time down so we get a little bit extra accuracy. Take a reading every 1 second. Here we go. So it's still trending down. So what we're going to do is I'm going to let this fully warm up. I got to give it a couple of hours. The rubidium is good. It's locked in. It's been on for weeks. It's also been synced up to the GPSDO, and the GPSDO is locked. What we're going to do is let this warm up. It'll run for probably most of the rest of the night. Might tweak it right before I turn in, which will be around 6 hours of warm-up. So crystals and things like that take a while to get heat soaked. My 184, you don't align the crystal if it hasn't been on for at least 6 hours. So definitely want to get this as accurate as possible, given the time base that's in it. So with that, now all I have to do is wait, and we'll be back in a while. I am going to slip the cover back over it. That way it, if the lab cat hops up on the bench and decides to try to sniff something, she doesn't stick her nose in 400 volts. Okay, we have come down significantly in frequency. So this means the internal oscillator is running a little fast. So what we're going to do is finish up the calibration. This is actually a soft calibration. It says all we're supposed to do is press one of the arrow keys. Oh, that doesn't work. So let's check the service manual. Okay, to get to the calibration menu, you have to press Scale and Offset while turning on the units, Cal Secure. Okay, after putting in the cal code, we've gotten cal unsecured, so we've unsecured. No, we don't want cal count. We want time base. So we do want calibrate time base, which is what we're looking for. Okay, supply 10 megahertz channel 1. This is 10 megahertz off of the rubidium. And enter. Okay, so we have time-based calibration passed, which is what we were looking for. And after entering a new code, which can be anything, just remember it, we're back to cal secured. So the time base should be calibrated now. We'll turn this off, turn this back on. We should see closer to 10 megahertz. Well, that looks better. Well, I would say that's going to be a success. So we've redefined what 10 megahertz is for this particular unit. I did not have to adjust the pot on the side of the high stability time base, and you shouldn't. So the oscillator inside is electrically driven based off of that calibration procedure. So the pot that's on the time base, you could dial a perfect 10 megahertz, but then it will fail a time base cal. So because this was set correctly, everything's good to go. It just goes to show how sensitive some of these oscillators are. The quick power off till you put the bumpers back on, it danced around a little bit before it came back and settled. So it should settle back around 10 megahertz, but it's going to take a while to get there for the warm-up. So, as always, the dish of shame. These are the caps we took off of the board and the power supply. We did find that they were starting to leak and definitely need to get done, but this will keep this frequency counter going, or universal counter going, for quite some time in the future. So with that, I will see everybody in the comments in between videos. If you like what you see, subscribe. Patreons are running about 3 videos ahead right now. So if you want a little bit more content, head over and check out the Patreon page. And I will see everybody in the next video. As always, more is on the way.